Let's take a quick tour of some of the properties of infinite series. This is copied from Theorem 8.2.3, which has a bit more detail, so you should really go read it, but I just want to give the high-level overview here. We've already used this idea that if you have a constant times each term, you can pull that constant out in front of the sum and just get the constant times the series, so that's fine. And then the sum and difference rule, the sum of individual terms added up is the sum of this one plus the sum of that one. No big surprise. Same thing for differences. But here's the big question that the theorem doesn't talk about. Does it work to do this for products? If I have the product of an times bn as a sum of that, is that equal to the sum of the a's times the sum of the b's? Or if I have this, can I just rewrite it like that? And does it work for quotients too? So that's the big question. Take a sec to think about whether you think that works. The answer is this hardly ever works. So let's write that in big red letters. So you can come up with examples where it's true, like if all the a's are 0 and all the b's are 0, then sure, the sum of the zeros times the sum of the zeros works out. But for any reasonable series that we're interested in, it's usually complicated enough that you can't just apply this rule. So that's something to watch out for. Key idea 8.2.1 has a bunch of important series like the sum of 1 over n factorial, the sum of 1 over n squared, which has a surprise to it. So I recommend you see the book there. There's not much for me to copy out. The book has it just as well as I could copy it out. Let's take a look at Theorem 8.2.4, which is called the nth term test for divergence, which says if the sequence terms aren't going to 0, converging to 0, then the sum diverges. Notice this does not say that if the terms are going to 0, then the sum converges. The harmonic is one proof of that, where the individual terms, 1 over 1, 1 over 2, 1 over 3, are going to 0, but the sum does not converge. So it's a very careful statement that if this is true, then this is true. But it doesn't mean that it goes backwards. It doesn't mean that if this is true, then that's true. And it doesn't mean if this is not true, then this is not true. It's interesting, you don't have to know this, but we didn't have this theorem for infinite integrals. It turns out there are integrals where the integrand, little f of x, doesn't converge to 0. It actually oscillates in a particular way, but the integral still converges. But here where we've got only integer points, then we don't have to worry about integer x values. So let's wrap up and talk about testing series for convergence here in chapter 8.2, basically saying what have we seen so far. We just saw, what's the name of this idea? If the sequence converges, it doesn't converge to 0, then the series diverges. That's the nth term test, which we just saw right up there. If you have a sequence and you can write it as a geometric, and you can identify r, and the absolute value of r is less than 1. That means r is between -1 and +1, not including -1, not including +1. Then you can stop and say the series converges, and you can use that formula 1 over 1 minus r. But you might have to undo some of the stuff you did to rewrite it as a geometric, like moving a constant out front or something. If absolute value of r is greater than or equal to 1, then you can stop and say the series diverges, and then you should not use 1 over 1 minus r because it will give you a finite answer when the actual answer is not any particular finite number. Can you think of it as a p series, like 1 over n to the p, including harmonic? If you can, then you can determine whether the series converges or diverges. But unless it's really special, like p equals 2, we can't determine what the series converges to. There's no nice formula unless p is 2, 4, 6, 8, etc. Even the odd numbers, p equals 3, there's no nice formula for what that series converges to. And then if none of those work, you might think, well, maybe this is a telescoping series. And if it is, that doesn't tell you whether the sum converges or diverges. You have to actually write a formula for s sub n and take the limit as n goes to infinity and see what that tells you to figure out whether the sum converges or diverges. If the sum converges, then this whole process usually gives you the answer, the final limit value. So that's a kind of grand overview, and in the next video we'll kind of put all these ideas to work on a few examples.